Hello and welcome to another Let's Study video. This video will be on Chapter 3, Computation, for the book Programming Principles in Practice using C++, 3rd edition. This chapter presents the basics of computation. In particular, we discuss how to compute a value from a set of operands, an expression, how to choose among alternative actions, selection, and how to repeat a computation for a series of values, iteration. We also show how a particular sub-computation can be named and specified separately, a function. Our primary concern is to express computations in ways that lead to correct and well-organized programs. To help you perform more realistic computations, we introduce the vector type to hold sequences of values. So we have Section 1 on computation, Section 2 on objectives and tools, Section 3 covering expressions with constant expressions and operators. Section 4 covers statements with selection and iteration. Section 5 covers functions, why we bother with functions, and function declarations. Section 6 covers the useful data type vector, which covers traversing a vector, growing a vector, a numeric example, and a text example. And finally, in Section 7, we cover language features. So we have Chapter 3, Section 1, Computation. From one point of view, all that a program ever does is to compute. That is, it takes some inputs and produces some outputs. After all, we call the hardware on which the program runs a computer. This view is reasonable as long as we take a broad view of what constitutes input and output. So we have a graphic here showing us two squares, input, output, with a big orange square covering code. Labeled code, often messy, lots of code, and we have some data within this code block. The input can come from a keyboard, from a mouse, from a touchscreen, from files, from other input devices, from other programs, from other parts of a program. Other input devices is a category that contains really interesting input sources. Music keyboards, video recorders, network connections, temperature sensors, image sensors, power supplies, etc. To deal with input, a program usually contains some data, sometimes referred to as its data structures or its state. For example, a calendar program may contain lists of holidays in various countries and a list of your appointments. Some of that data is part of the program from the start. Other data is built up as the program reads input and collects useful information from it. For example, the calendar program will probably build your list of appointments from the input you give it. For the calendar, the main inputs are the request to see the months and days you ask for, probably using mouse clicks, and the appointments you give it to keep track of, probably by typing information on the keyboard. The output is the display of calendars and appointments, plus the buttons, and prompts for input that the calendar program writes on your screen. In addition, the calendar may send you reminders and synchronize with other copies of the calendar programs. Input comes from a wide variety of sources. Similarly, output can go to a wide variety of destinations. Output can be to a screen, to files, to network connections, to other output devices, to other programs, and to other programs of a program, or other parts of a program. Examples of output devices include network interfaces, music synthesizers, electric motors, light generators, heaters, etc. From a programming point of view, the most important and interesting categories are to and from another program and to and from other parts of a program. Most of the rest of this book could be seen as discussing the last category. How do we express a program as a set of cooperating parts, and how can they share and exchange data? These are key questions in programming. We can illustrate that graphically. So we have a graphic here, which shows input going into a large set with 3 blocks of different code with their own set of data, and using input and output between the code to eventually produce some output. The abbreviation I/O stands for input-output. In this case, the output from one part of code is the input for the next part. What such parts of a program share is data stored in main memory on persistent storage devices, such as disks, or transmitted over network connections. By parts of a program, we mean entities such as a function producing a result from a set of input arguments. For example, a square root from a floating point number, a function performing an action on a physical object, for example, a function drawing a line on a screen, or a function modifying some table within the program. For example, a function adding a name to a table of customers. When we say input and output, we generally mean information coming into and out of a computer. But as you see, we can also use the terms for information given to or produced by a part of a program. Inputs to a part of a program are often called arguments, and outputs from part of a program are often called results. By computation, we simply mean the act of producing some outputs based on some inputs, such as producing the result output 49 from the argument input 7 using the computation function square. See section 5, chapter 3. As a possible helpful curiosity, we note that until the 1950s, a computer was defined as a person who did computations, such as an accountant, a navigator, or a physicist. Today, we simply delegate most computations to computers of various forms, such as smartphones. Chapter 3, Section 2, Objectives and Tools. Our job as programmers is to express computations correctly, simply, and efficiently. Please note the order of those ideals. It doesn't matter how fast a program is if it gives the wrong results. Similarly, a correct and efficient program can be so complicated that it must be thrown away or completely rewritten to produce a new version or release. Remember, useful programs will always be modified to accommodate new needs, new hardware, etc. Therefore, a program and any part of a program should be as simple as possible to perform its task. For example, assume that you have written the perfect program for teaching basic arithmetic to children in your local high school or your local school. And that its internal structure is a mess. Which language did you use to communicate with the children? English? English and Spanish? What if I'd like to use it in Finland, in Kuwait? How would you change the natural language used for communication with a child if the internal structure of the program is a mess and logically simple, but in practice almost always very difficult? Operation of changing the natural language used to communicate with users becomes insurmountable. We have an advice alert marker. Concerns about correctness, simplicity, and efficiency become ours the minute we start writing code for others and accept the responsibility to do that well. That is, we must accept that responsibility when we decide to become professionals. In practical terms, this means we can't just throw code together until it appears to work. We must concern ourselves with the structure of the code. Paradoxically, concerns for structure and quality of code are often the fastest ways of getting something to work. When programming is done well, such concerns minimize the need for the most frustrating part of programming, debugging. That is, good program structure during development can minimize the number of mistakes made and the time needed to search for such errors and remove them. Then we have a core concept, alert marker. Our main tool for organizing a program and for organizing our thoughts as we program is to break up a big computation into many little ones. This technique comes in two variations. Abstraction. We hide details that we don't need to use. A facility. Implementation details behind a convenient and general interface. This technique comes in two variations. Abstraction. We hide details that we don't need to use a facility behind a convenient and general interface. For example, rather than considering the details of how to sort a phone book, thick books have been written about how to sort. We just call the sort algorithm from the C++ standard library. All we need to know to sort is how to invoke or call that algorithm. So we can write sort B, where B refers to the phone book. Sort is a version of the standard library sort algorithm. See section 5 of chapter 21. Another example is the way we use computer memory. Direct use of memory can be quite messy, so we access it through typed and named variables. See section 2 of chapter 2. Standard library vectors, see section 6 of chapter 3, and maps, see section 2 of chapter 20, etc. And the other variation of this technique of breaking up computation into little ones is divide and conquer. Here we take a large program or a large problem and divide it into several little ones. For example, if we need to build a dictionary, we can separate that job into three parts. Read the data, sort the data, and output the data. Each of the resulting problems is significantly smaller than the original. And we have a warning alert marker here. Why does this help? After all, a program built out of parts is likely to be slightly larger than a program where everything is optimally merged together. The reason is we are not very good at dealing with large problems. The way we actually deal with those, in programming and elsewhere, is to break them down into smaller problems. We keep breaking those into even smaller parts, until we get something simple enough to understand and solve. In terms of programming, you'll find that a first attempt of a 1,000-line program has far more than 10 times as many errors as a 100-line program. So we tried to compose the 1,000-line program out of parts with fewer than 100 lines. For large programs, say 10 million lines, applying abstraction and divide and conquer is not just an option, it is an essential requirement. We simply cannot write and maintain large monolithic programs. One way of looking at the rest of this book is as a long series of examples of problems that we need to be broken up into smaller parts together with the tools and techniques needed to do so. When we consider dividing up a program, we must always consider what tools we have available to express the parts and their communications. A good library, supplying useful facilities for expressing ideas, can crucially affect the way we distribute functionality in different parts of a program. We cannot just sit back and imagine how best to partition a program. We must consider what libraries we have available to express the parts and their communication. It is early days. It is early days yet, but not too soon to point out that if you can use an existing library, such as the C++ standard library, you can save yourself a lot of work, not just on programming, but also on testing and documentation. The I/O streams save us from having to directly deal with the hardware's input-output ports. This is a first example of partitioning a program using abstraction. Every new chapter will provide more examples. Note the emphasis on structure and organization. You don't get good code just by writing a lot of statements. Why do we mention this now? At this stage, you, or at least many readers, have little idea about what code is, and it will be months before you are ready to write code upon which other people could depend for their lives or livelihood. We mention it to help you get the emphasis of your learning right. It is very tempting to dash ahead, focusing on the parts of programming that like what is described in the rest of the chapter are concrete and immediately useful, and to ignore the softer, more conceptual parts of the art of software development. However, good programmers and system designers know, often having learned it the hard way, that concerns about structure lie at the heart of good software, and that ignoring structure leads to expensive messes. Without structure, you are, metaphorically speaking, building with mud bricks. It can be done, but you'll never get to the 10th floor. Classical mud bricks lack the structural strength for that. If you have the ambition to build something reasonably permanent, or something large, you pay attention to matters of code structure and organization along the way, rather than having to come back and learn them after failures. We have section 3 of chapter 3 on expressions. What is that noise? Okay. Ignoring that, we have a core concept alert marker. The most basic building block of programs is an expression. An expression computes a value from a number of operands. The simplest expression is simply a literal value, such as 10, or the character A, or 3.14, or Norva. Names of variables are also expressions. A variable represents the object of which it is the name. Consider int length equals 20, a literal integer used to initialize a variable, int width equals 40, int area equals length times width, multiplication. Here the literals 20 and 40 are used to initialize the variables length and width. Then length and width are multiplied. That is, we multiply the values found in length and width. Here, length is simply shorthand for the value found in the object named length. Consider also length equals 99, assigning 99 to length. Here, as the left-hand operator of the assignment, length means the object named length, so that the assignment expression is read, put 99 into the object named length. We distinguish between length used on the left-hand side of the assignment or an initialization, the L value of length, the object named length, and length used on the right-hand side of an assignment or initialization, the R value of length, the value of an object named length, or just the value of length. In this context, we find it useful to visualize a variable as a box labeled by its name. With the graphic we've seen before, we have a blue box with int at the top, length on its left-hand side, and 99 stored within the box. That is, length is the name of an object of type int, containing the value 99. Sometimes, as an L value, length refers to the box object, and sometimes as an R value, length refers to the value in that box. We can make more complicated expressions by using operators, such as the plus sign, the divide, what is that? Is that the plus sign? Yep. That's plus and asterisk in just the way that we are used to. When needed, we can use parentheses to group expressions, such as the int perimeter equals the length plus width times 2, with length and width being within a set of parentheses. Without parentheses, without parentheses, we would have to Without parentheses, we'd have had to say int parameter equals length times 2 plus width times 2, which is clumsy, and we might even have made this mistake. We have int parameter equals length plus width times 2, which we add width times 2 to length. This last error is logical and cannot be found by the compiler. All the compiler sees is a variable called parameter, initialized by a valid expression. If the result of that expression is nonsense, that's your problem. You know the mathematical definition of a parameter, but the compiler doesn't. The usual mathematical rules of operator precedence apply. So, length plus width times 2 means length plus the product of width times 2. Similarly, A times B plus C divided by D equals the product of A times B plus the product of C divided by D, and not A times the sum of B plus C divided by D. See CPP reference for an operator precedence table. The first rule for the use of parentheses is simply, if in doubt, parenthesize. But please do learn enough about expressions that you are not in doubt about A times B plus C divided by D. Overuse of parentheses, as in A times B within parentheses plus C divided by D in parentheses, decreases readability. Why should you care about readability? Because you, and possibly others, will read your code. Ugly code slows down reading and comprehension. Ugly code is not just hard to read, it is also much harder to get correct. Ugly code often hides logical errors. Don't write absurdly complicated expressions, such as A times B plus C divided by D times E divided by negative F divided by G within parentheses divided by H plus 7. Too complicated. Took me a minute to figure out how to say that. And always try to choose meaningful names. And we go into constant expressions with subsection 1. Programs typically use a lot of constants. For example, a geometry program might use pi, and an inch to centimeter conversion program will use a conversion factor such as 2.54. Obviously, we want to use meaningful names for those constants. As we did for pi, we didn't say 3.14159. Similarly, we don't want to change those constants accidentally. Consequently, C++ offers the notation of a symbolic constant. That is, a named object to which you can't give it a new value after it has been initialized. For example, we have the const expression keyword, const expr, no space, double pi equals 3.14159, and we have a statement here, pi equals 7, which we would get an error, assignment to a constant, and we have double c equals 2 times pi times r, which is okay, we just read pi, we don't try to change it. Such constants are useful for keeping code readable. You might have recognized 3.14159 as an approximation of pi if you saw it in some code, but you would never have recognized 299,792,458. Also, if someone asked you to change some code to use pi with the precision of 12 digits for your computation, you could search for 3.14 in your code, but if someone incautiously had used 22 divided by 7, you probably wouldn't find it. It would be much better to just to change the definition of pi to use the more approximate value. Just the cont expression double pi equals 3.14159265359. We have an advice alert marker. Consequently, we prefer not to use literals, except very obvious ones, such as 0 and 1, in most places in our code. Instead, we use constants with descriptive names. Non-obvious literals in code outside definitions of symbolic constants are devised or derisively referred to as a magic constant. And by the way, 299,792,458 is one of the fundamental constants of the universe, the speed of light in vacuum measured in meters per second. If you don't instantly recognize that, why would you expect not to be confused and slowed down by other literals embedded in code? Avoid magic constants. A const expression, symbolic constant must be given a value that is known at compile time. A constant expression, for example, const expression int max equals 100. Int n cn get from operator n. Const expression int c1 equals max plus 7. This is okay, because c1 is, well, this is okay, and c1 is now 107. Const expression int c2 n plus 7 is an error. We don't know the value of n at compile time. We need that from the input of the user. To handle cases where the value of a constant that is initialized with a value that is not known at compile time but never changes after initialization, C++ offers a second form of constant, a const. In which case we have int n, cn get from cn, place into n, and we have a const int c3 equals n. And this is okay. But after we have given c3 a value, c3 trying to change c3, such as in c3 equals 7 statement, we get an error. c3 is a const. Such const variables are very common for two reasons. C++ version 98 did not have const expression, so people use const. Variables that are not constant expressions, their value is not known at compile time, but do not change values after initializations, are themselves widely useful. Oh, no. There we go. And I ate way too much, making it difficult to keep an appropriate amount of air in my lungs for speaking comfortably in a reading tone. Alright, subsection 2 of section 3 of chapter 3. We just use the simplest operators. However, you will soon need more as you want to express more complex operations. Most operators are conventional, so we'll just explain them later as needed, and you can look up details if and when you find a need. Here are some common operators. We have an example of lval equals a, which is the assignment operator, not to be confused with the double equals equality operator. We have ++lval, which is the pre-increment and use the incremented value. So we increment that value and then we use it. We have --lval, which is the pre-decrement, which we decrement and then use the decremented value. We have the exclamation mark a, which is the not operation, which is the result is a bool. So if a is true, not a equals false. If a is false, not a equals true. We have the unary minus operator, which I believe it's not written here, but it negates. It sort of makes a positive into a negative to a positive. Looks like there's no comment here about it. We have a asterisk b, which is the multiply operation. We have a divided by b, which is the divide operation. We have a %b, which is the modulo or remainder, and this is only available for integer types. We have a plus b, which is the add operation. A minus b, which is the subtraction operation. We have out, get from operator b, which we write b to out. No, that's not the get from. That's the That's the output operator. Output operator B, which writes B to out, where out is the O stream, the output stream. We have in, get from operator B, which we read from in into B, where in is an I stream, or an input stream. L value times equals A. This is a compound assignment. Well, L value equals the L value times A. Also available for divide, modulo, add, and minus. Add and subtract. F of A is a function call where we pass A to F as an argument. We'll see that in section 5 of this chapter. We have F T, T in angle brackets, with A. So F of T of A, we have a function template call. We pass A to F of T as an argument. We're going to see that in section 2 of chapter 21. We have, what is this? It's the lambda expression, something I actually don't know. We have brackets containing brackets followed by A in parentheses followed by S in curly brackets. We create a function taking A as an argument. All right, well, that doesn't really explain much, but I guess we're going to learn that in chapter 21. We use LVal, short for L value. That is a value that can appear on the left-hand side of an assignment, where the operator modifies an operand. Example, we have A less than B, which is the less than operator. The result is a Boolean value, a bool. We have A less than or equal to, which its result is a bool. All these are result to the bool, except for the bottom. We have A greater than B, A greater than equal to B, A equal to B, A does not equal B, A and ampersand symbol, which is logical and A vertical bar, which is a logical or, and we have T of A in curly braces, which is the widening conversion. The result of the value A is converted to type T. See CPP reference for a complete list of operators. For example, of the use of the logical operators double ampersand and double vertical bar or the explanation not. We see that in chapter 4, 6, and 9. We have an alert marker here. Note that A less than B less than C means A less than B in parentheses less than C, and that A less than B evaluates to a Boolean value true or false. So A less than B less than C will be the equivalent of either true less than C or false less than C. In particular, A less than B does not mean A less than B less than C does not mean is B between A and C, as many have naively and not unreasonably assumed. Thus, A less than B less than C is basically a useless expression. Don't write such expressions with two comparison operations, and be very suspicious if you find such expression in someone else's code. It is likely an error. An increment can be expressed in at least 3 ways. We have the pre-incremental operator on A, so we have plus A. We have A plus equals 1 and a equals a plus 1. We have the advice alert marker. Which notation should we use? Why? We prefer the first version, plus plus a, because it more directly expresses the idea of incrementing. It says what we want to do, increment a, rather than how to do it. Add 1 to a, then write the result to a. In example, a way of saying something in a program is better than another if it more directly expresses an idea. The result is more concise and easier for a reader to understand. If we wrote a equals a plus 1, a reader could easily wonder whether we really meant to increment by 1. Maybe we just mistyped a equals b plus 1, a equals a plus 2, or even a equals a minus 1. With plus plus a, there are far fewer opportunities for such doubts. Please note that this is a logical argument about readability and correctness, not an argument about efficiency. Contrary to popular belief, modern compilers tend to generate exactly the same code for a equals a plus 1 as for plus plus a, where a is one of the built-in types. Similarly, we prefer a times equals scale over a equals a times scale. And we have section 4 of chapter 3 on statements. An expression computes a value from a set of operands using operators like the ones mentioned in section 3. What do we do when we want to produce several values? When we want to do something many times. When we want to choose among alternatives. When we want to get input or produce output. In C++, as many languages, you use language constructs called statements to express those things. So far, we have seen two kinds of statements: expression statements and declarations. An expression statement is simply an expression followed by a semicolon. For example, a equals b, and the pre-increment operator plus plus c. Those are two expression statements. Note that the assignment equals is an operator so that a equals b is an expression we need the terminating semicolon to make a equals b a statement. Why do we need those semicolons? The reason is largely technical. Consider a equals b plus plus c semicolon. So this would generate a syntax error, missing semicolon. Annoyingly, it would do it on this. It would do it on this line. Without the semicolon, the compiler doesn't know whether you mean a equals b plus plus semicolon c semicolon or a equals b semicolon plus plus c semicolon. Such problems are not restricted to computer languages. Consider the exclamation, "Man eating tiger." Who is eating whom? Punctuation exists to eliminate such problems. We have man dash eating tiger. For when statements follow each other, the computer executes them in an order in which they are written. For example, int a equals 7 and cout, output operator a, output operator new line character. Here the declaration with its initialization is executed before the output expression statement. In general, we want a statement to have some effect. Statements without effect are typically useless. For example, 1 plus 2 statement and a times b statement. Such statements without effects are typically logical errors, and compilers often warn against them. Thus, expressions Expression statements are typically assignments, input-output statements, or function calls. We will mention one more type of statement, the empty statement. Consider the code. If x is equal to 5, y equals 3. Well, if x is conditionally equal to 5, we assign 3 to y. This looks like an error, and it almost certainly is. The semicolon in the first line is not supposed to be there. Oh, we have a warning alert marker here. But unfortunately, this is a legal construct in C++. It is called an empty statement. A statement does nothing. An empty statement before a semicolon is rarely used. What will happen if this code is run? The compiler would test x to see if it has the value 5. If this condition is true, the following statement, the empty statement, will be executed with no effect. Then the program continues to the next line, assigning the value 3 to y, which is what you wanted to happen if x equals 5. If, on the other hand, x does not have the value 5, the compiler will not execute the empty statement, still no effect, and will continue as before to assign the value 3 to y, which is not what you wanted to have happen unless x equals 5. In other words, the if statement doesn't matter. Y is going to get the value 3 regardless. This is a common error for novice programmers, and it can be difficult to spot, so watch out for it and hope your compiler warns. The next section is devoted to statements used to alter the order of evaluation to allow us to express more interesting computations than those we get by just executing statements in the order in which they are written. We have section 4, subsection 1, selection. In programs, as in life, we often have to select among alternatives. In C++, this is done using either an if statement or a switch statement. Subsection 1 of subsection 1 of section 4 of chapter 3, if statements. The simplest form of selection is an if statement, which selects between two alternatives. For example, int a equals 0, int b equals 0. We print to cout. Please enter two integers. We prompt the user for two integers. We use cin in the getFrom operator to fill a and b with the integers we get from the user. And then if a is less than b, the condition, we print out a is smaller than b. And if not true, if else a is greater than b, which is the alternative, cout a, we print out that a is larger than or equal to b. We have the first alternative is that a is less than b, and then we have the second alternative where a is larger or equal to b. We have a core concept, alert marker. An if statement chooses between two alternatives. If its condition is true, the first statement is executed, otherwise the second statement is. This notion is simple. Most basic programming languages features are. In fact, most basic facilities in a programming language are just new notation for things you learned in primary school, or even before that. For example, you were probably told in kindergarten to cross the street at the traffic light. You had to wait for the light to turn green. If the traffic light is green, go. And if the traffic light is red, wait. In C++, that becomes something like, if traffic light is equals green, go. And if traffic light is equal to red, wait. I just grabbed my mouse and went to scroll as if I were to scroll my recording screen as if I could scroll down the book. Yeah, no, I got a document camera in my hands to do this. So, the basic notation is simple, but it is also easy to use if statements in a too simple-minded manner. Consider what's wrong with this. So we have two comments here. We convert from inches to centimeters or centimeters to inches, and a suffix I or C indicates the unit of the input. So we have the const expression double centimeters per inch is equal to 2.54. So an inch equals 2.54 centimeters. We have the double length is equal to 1. We have the character unit is, I guess, the empty character. And we have cout, prompting the user to please enter a length followed by a unit, either C or I, for centimeters and inch. We get in, C in, where we grab length and unit that we just prompted for. If the unit is equal to I, cout, we print out the length in inches equals the conversion rate. So length that we got from the user times the conversion to centimeters. And if that statement, unit is equal to I, is not true, we print out cout the length as centimeters equals the reverse, so the multiplicative inverse of the centimeter per inch to length. So we're going to divide it. So length divided by the centimeter per inch to get inches. We print out the inch. Actually, this program works roughly as advertised. Enter 1 I, and you get 1 inch equals 2.54 centimeters. Enter 2.54 C, and you'll get 2.54 centimeters equals 1 inch. Just try it. It's good practice. Ah, crap. All right, well, we hit our first try it. Whee! You get the program. All right. Grab the keyboard. All right, let's shrink that down. Try a new project. Grab the keyboard. Okay. All right, I'm just gonna hide the webcam. And we have PPP3 underscore. Try this. What should we call this? If statement. Centimeter to inch. Then we go to source files and add a new item, main.cpp. And then we're going to right click, go to our project properties, go to C/C++, go to general, scan sources for module dependencies, make that yes. Go to language, C++ language standard, bring that to C++ latest, and then build ISO C++23 standard library to yes, and apply these changes. This program converts centimeter to inches or inches to centimeters, depending on input from user, but hides a flaw, logical flaw. So we want to import std using, we use an std namespace into main. Turn 0. const expression. What is it? Double ow. Where's my bones? Double centimeter per inch equals exactly 2.54. We have the double length equal to 1 char unit I say unit selection equals the nothing character. Is that not an option? Alright, the space character. Alright, let's prompt to the user. Please enter a length followed by a unit. C for centimeter, I for inch. And then we grab from CN the length value as well as the unit selection. Then if unit selection is equal to I for inch, you want to print out the length is equal to the length in inches the length times the centimeter per inch and else we want to print the length as centimeters equal to the length value divided by instead the centimeter per inch constant inch. And that's our program. Let's give it a go. Let's try 1 inch equals 2.5 centimeters. That works. If we try the other example, 2.54 C. We have 2.54 centimeters equals 1 inch. So it works, but I'm thinking what we're going to be shown is that if we enter in 1F, we have 1 centimeter. Well, what's F? F isn't C, F isn't I, and that's the problem. We didn't account for the user giving us an unknown unit selection. let's go back to the book. Keyboard aside. The snag is that we didn't test for bad input. The program assumes, well, I was right. The program assumes that the user enters proper input. The condition unit equals the character I distinguishes between the case where the unit is I and all other cases. It never looks for a C. What if the user entered... Oh, I used F too. What are the chances? We have 15F for feet. Just see what happens. Well, we actually did that earlier. It thinks it's a centimeter. The condition unit equals I would fail, and the program would execute the else part, the second alternative, converting from centimeters to inches. Presumably, that is not what we wanted when we entered F. We have an advice alert marker here. We must always test our programs with bad input, because someone will eventually, intentionally or accidentally, enter bad input. A program should behave sensibly even if its users don't. Here is an improved version of the if statement. So we check if it's I, we check if it's C, and we check if it's not I or C. We first test for unit I and then test for unit C, and if it isn't either, we say sorry. It may look as if we used an else if statement, but there is no such thing in C++. Instead, we combine two if statements. The general form of an if statement is if expression statement, else statement. That is an if followed by an expression in parentheses, followed by a statement, followed by an else, followed by a statement. We used an if statement as the else part of an if statement. Oh, that's cool. So we have if expression statement, else statement. That statement here is being used. That's this. It's another one. It's just another one. Oh, that's cool. There is no elif. It's just else if. That's cool. For our program, that gives us this structure. If unit equals I, we go to our first alternative. If unit is C, we go to the second alternative, and else we have our third alternative. That's cool. I didn't know that. I thought the else if was its own thing. We have an advice alert marker here. In this way, we can write arbitrarily complex tests and associate a statement with each alternative. However, please remember that one of the ideals of code is simplicity rather than complexity. You don't demonstrate your cleverness by writing the most complex program. Rather, you demonstrate competence by writing the simplest code that does the job. Okay, so we have this try this. Use the example above as a model for a program that converts yen, y, to kroner, k. That converts yen, kroner, and pounds into dollars. If you like realism, you can find conversion rates on the web. If you like realism, I very much like realism. Okie dokie. So let's copy this program into the next one. So let's grab main. Copy. Let's create a new project. New empty project. PPP3. Try this. Currency converter. Go here. File Explorer. drop in the main PPP, CPP, add that existing one. Go to project properties, make our usual changes. Yen. Kroner. More pounds to dollars. I don't know what kroner is, to be very honest. Alright, let's get these conversion rates. Yen to USD. So, amount. Currency. Yen to dollar. $1 0067 USD. Kroner. Danish krone. Okay. Pound to dollar. 1 pound equals 1.35 USD. Whoops. Man, these are vastly different sizes. Amount. Okay, let's test this out. I think it works. Should work. High hopes. So, 1 yen. Uh-oh, that didn't work. Also, that broke. That shouldn't be there. Why didn't it know what yen is? Do I have to 1, 2, why? Why doesn't it know what the yen is? What? Oh. Yeah. Oh. True. Converted. Yeah. Hmm. Unicode? Yeah, Unicode. Why is this failing? Alright, actually, I don't think we need that. That's okay. But why is this failing? Why is wchar not working with cout? Let's give this a go. 1 yen. Nope. Give this a go. Nope. Why? Why no work? Just want to see it. Huh? Nothing. And why? Uh-oh. Is it possible that it is represented differently in console? This is the code page. WGL4 character set. Original IBM PC. Yeah. Yep. Although, now it has the yen. Checking it out. We got the yen. Perhaps we need to use this one instead. Give this a go. Not that I can see a difference. 1Y. Nope. Still not displaying correctly. showing up correctly here. 165 value. That's well within the char limits. Well, actually, no. How many characters does ASCII have? $128. Okay, so it is above char. But thought I got around that using WC out. Going on wide character. Thing is, I'm using wide characters, but the command prompt isn't. I guess. So we have this here, which is the value 165. And when we try to print it, on Y, we get this character, which is what code? This guy. So let's go check it out. We're 165. Yeah, we're getting this guy. Uppercase N with tilde. We don't want that one. We don't want that one. We want the N, the 157. Okay, so how do we get the debug console to accept Unicode? I see a command someone's providing. So let's try it. Let's go here to our program. Open a command prompt here. Okay. Right click, properties, options, UTF-8. Okay, so that's working. But here's a problem. Or is it a problem? Check the properties. Yeah, it's back to OEM. We don't want it OEM. We want it always to be Unicode. Automatically. How do we do that automatically? Register value time. Okay. H key, current user, console. is no code page here. We can make a new one. A D word? Code page. Decimal. 65. Oop. 65001. Okay. X. Close. HCP. Woo! Oh, baby, we got it working. Let's go back to our program now. Don't need that no more. Please work. 1Y. Sha. Why? Why no egg? Oh, it's a different. What is this? C programs, Microsoft Visual Studio Community Edition. Is this his own command prompt? Hold on. Yep. Well, did that work? Huh. Ah, thanks.
I swear, text is always the bane of my existence. Where is this? I can see it, but I can't see it. Okay. Oh, it's probably right here. Oh crap. What was it called? Code page. $65,001. Close. Okay. Close. Rerun. 1 yen. 1 nothing. It broke. It completely broke. One yen. Oh, did I break something bad? Let's try this again. Properties. Options. It's working. We're broke. Properties. The font. We need Lucidia console. Then 1Y. It didn't work either. For the love of everything, please. Why didn't it work? Face name, Lucidia console. Okay, well, that looks good. Find a work. Close the application. One by nothing. Like it didn't even print it. Seriously. It's not even there. We're making negative progress. Like it didn't even print this and just stopped. One, just nothing else. Why it's broken? Oh, this sucks. Well, welcome to programming. For the love of God. Well, at least we're back to where we were. Even though that's not where I want to be. I guess we're going to skip having special characters. Really want it to work. Gotta add a new one. Let's try this. Nope. Oh, everything breaks. Everything breaks. I'm gonna lose my mind. I don't like this at all. I don't like this.
I don't want to give up. I don't understand why it's not working. I changed the registry to put the proper code page. The code page is UTF-8, which should include the yen symbol. And yet we get no output. Lucidia console, code page, UTF-8, 6501. It's UTF-8 compatible. Do we need a UTF-16? Okay, looks like I need to get that working. I'll see you guys in the next video. This will be a part 1 of 2. We'll finish off chapter 3 after we get this working. I'll stop the recording in order to restart, and we'll start off from there.